Well, I didn't say a whole. We didn't get very far. We're about 7 minutes in. It's a good call. Sorry about that. But basically, I just went over geometric optics, and I described what an image is. An image is just defined by a position, a size, and the orientation of what we're seeing. So where is the thing that we're seeing, i.e., where does it appear to be? Where does it appear to be? How big does the thing appear to be? What orientation does the thing appear to have? And so what we can do is we can describe an object. Typically in physics, we just draw it as an arrow. And so the arrow's direction is its orientation, its length is its size, and its position is and its horizontal position is its position. Hopefully this diagram is straightforward enough. If you get confused, if you're watching this later, go back and look at the lecture notes and spend some more time on it. But I'm going to answer the question now: what happens if we put an object between us and a mirror? So in this case, the mirror. So here's our eyeball. We're going to put the object. The object is our arrow, and so I'm going to put a mirror, like say right here. I'm just going to draw a vertical line for the mirror. So in this case, what light rays are going to go from the object to our eyeball? Now, of course, we're going to see the object directly in front of us, but we're not interested in that image. We're interested in the image that comes from the mirror. So one light ray will go from, let me draw it in color. One light ray will go from the object to the mirror and then bounce back. Let me draw it in a different color. And go straight to our eyeball, right? So that's one light ray. Another light ray, say, if we remember the idea that we use when we're talking about geometric optics is we figure out where the light rays would all seem to converge if we had a bunch of different perspectives. So we want to figure out the intersection points of all these light rays. So let's put another eyeball here. Say, where does the light ray go there? Well, in order to get a light ray from the object to that eyeball, we would have one light ray. Let's draw a straight line. One light ray that goes here, hits the mirror, and then bounces off using the law of reflection, and goes to the eyeball. So now the question is, what happens? So where is this point of intersection? Well, it turns out that these two light rays that are coming back, they don't actually intersect anywhere, right? The red light rays don't intersect. Instead, what happens is they appear to intersect somewhere else. This is not a very good drawing, I'm sorry. They would appear to intersect behind the mirror at this point. So in this case, we would have an object here, and we could figure out that it indeed has the same height and stuff if we did the same sort of ray tracing for the bottom of the arrow. But in this case, this object, or this image, is the apparent source of light rays. The idea here is that if you were to move all around this way, it would always look like light rays were coming from that point there behind the mirror. And that's why when you look at a mirror, it looks like there's something on the other side of it, right? It looks like there's something twice the distance away. And in fact, if I had done this perfectly, this distance and this distance would have been the same. So this is a bad drawing. In the lecture notes, it's a little bit better because that's a little bit more precise. Not bad lecture, bad drawing. So, so the idea here is to figure out where the image is. We view the rays from more than one location. And then we trace the rays back to their point of intersection. And sometimes those rays will actually intersect. I'm talking about the like the reflected rays. We don't trace, when I'm tracing, I'm not saying we do this. I'm saying we trace the rays in a straight line passing through whatever they may have passed through, but just imagine that they were going in a straight line instead. We trace them back to their point of intersection, and so sometimes these red rays, these outgoing rays, the rays that come after they interact with the mirror, those are the rays that we trace back, and sometimes they will actually intersect on our side of the mirror. And we'll get to this, but like if you have a curved mirror that's curved inward, sometimes it'll appear that something's in front of the mirror. Sometimes, like in this case, they will appear behind the mirror. Either one's okay, it's just in the event that it's behind the mirror, or behind the lens, or whatever, you might have to extend those rays as if they were actually continuing on, even though they don't. So this is all fine, and it's great that you can just use a ruler and a protractor and stuff to do these sort of analysis, but this is physics. It's not enough to just draw pictures. We do want to do some mathematics here, so then we can get precise answers for these types of questions, like where is the image produced with such and such a setup. So in order to do that, I'm going to introduce some sign conventions, SIGN conventions. And the reason I'm doing this is because it'll help us quantify various properties of an image. So first, we're going to define x equals 0 at the position of the mirror or the lens, or whatever. So this is the position from which all other positions are measured. So when we say, if we were to say that the object is at x equals 5, that means that it's 5 units away from the mirror in the horizontal direction, in a particular direction, either left or right, and I'll be more specific about what I mean by that. So the next question is, okay, so, let me be specific here. This is in the horizontal direction. You can think of the center of the mirror, like this point here. You could think of that as like the origin of our xy plane, if you wanted to. But it's not quite that straightforward, because x being positive or negative doesn't necessarily mean right or left always. In fact, that's where these sign conventions come from. The question might be, what values are positive or negative? So I'm going to draw this table a lot today. So I'm going to give you a table of sign conventions. So if we're interested in the object distance, the distance from the object to the mirror, we use the symbol S for that. S is just typically used for distance, and the distance that object is from the mirror is positive when the object is on the incoming side. And I'll explain what that means in a minute. Oh, come on. Move. We say that the distance S is negative when the object is on the other side, so not on the incoming side. That does not mean outgoing side, it just means the opposite side of the incoming side. The image distance, we could likewise characterize. This is the distance that the mirror is from the image. The symbol we attach to that notion is S prime, and in this case, it's positive when the image is on the outgoing side. And again, I'll be specific about what I mean by this. And again, it's negative when the image is on the other side. And so for now, this is what I will include in the table. We will add more things to this table later, so I'll probably copy and paste later. But the idea is we now have a way that we can describe the location of the object and the location of the image in terms of numbers, in terms of variables. So when I say incoming side, I need to specify what this means. I mean, this is the side of the mirror that light is on before it hits the mirror. So the light comes from the source, or comes from the object. It is on one side of the mirror, and then it hits the mirror. So the incoming side is the side of the mirror where the light starts. The outgoing side is the side that light is on after it hits the mirror. So after the light hits the mirror, it moves, it's traveling on one side of the mirror. That is the outgoing side. So let me give an example here. Let's go back to that picture of a mirror that we had earlier. So we have our eyeball. We have our object here. We have our mirror. So object comes in, goes back, hits eyeball. One light ray. Another light ray might do this. Typically, you don't actually have to draw all the eyeballs. It's not a thing that we have to do. And so if we want to, so this distance here, this distance is S. And if we wanted to find the location of the object, we would trace these back because those are the outgoing rays, the rays that travel after interacting with the mirror. They might intersect, say, here, and so we would have an image here. And so this distance would be S prime. Now the question is whether it's positive or negative. Oh, and this is the object, the actual source. And this is the image, or the apparent source. So the whole point of optics is that our eyes don't actually figure out where an object is. Our eyes tell us where it appears the light from the object is coming from. So with regards to a mirror, the object appears, the light from the object appears to be coming from a different place than it is because our eyes don't know that there's a mirror in the way. Similarly with lenses, our eyes don't know that there's a lens in the way. Instead, our brain just says, look, the thing is there because the light appears to be coming from that direction. So in this particular example, S is greater than 0 because using our sign conventions, the object is on the same side that the light starts on. That'll almost always be the case. There are some more complicated examples where that won't be true, but almost always S is positive. However, in this case, S prime is negative because it's on the other side of the side that's outgoing. So the outgoing side and the incoming side are the same in this case because it's a mirror. And so because the image is not on the incoming side, on the outgoing side, it's on the other side than the outgoing side, hence negative. So if we were to describe, if we were to say, we might say S prime is equal to -3 meters or something, and S might be equal to 2 meters. Turns out that they'll be the same, but you would just, like, it's a distance, so it has units of meters, and it has a number attached to it because it's a measurement, and it has a sign, positive or negative, and that sign means a certain thing. We could have chosen different sign conventions, but these sign conventions will make our calculations a lot easier. Okay, great. That's mirrors. Mirrors are relatively straightforward. There are other ways we can form images, though. We can form images via refraction rather than reflection. Remember, refraction is when the light bends because the index of refraction changes. So we can also redirect light via Snell's law, i.e. refraction. So the example here, and I'm actually going to just copy and paste this image from my lecture notes because it's actually kind of hard to draw, but I'll talk about it for a minute. Copy, paste. So let me talk about this image for a minute. So let's say that you have an object in some medium. So you have your object in some medium over here, it's the red light, or the red arrow. That object, maybe it's in a medium with a higher index of refraction. It's going to emit light as it does. Some of the light will reflect off of the interface, but we're not going to worry about that because that doesn't get to the other side of the That doesn't get to the other side of the interface, and our observer, we're assuming, is on the other side of the interface. By the way, if it reflected off of the interface, then it would just behave like a mirror. So we could put eyeballs over here, and it would just be like as if there was a mirror at the interface instead of a change in medium. So just keep that in mind. Anyway, so it can emit light straight, and we know that Snell's law tells us that if the incident angle is 0 degrees, and n1 sine theta 1 equals n2 sine theta 2. So if theta 1 is equal to 0, then theta 2 will be equal to 0. So when it comes in straight, nothing happens. The light just goes in straight. However, if we instead put an observer down here, if we were interested in what happens to light that gets to here, we would note that the light will bend. It bends outwards because it's going to a faster medium, and a medium with a lower index of refraction. And so what happens is if you were to put another eyeball here, you would say, okay, well, where does this light appear to be coming from? It appears to be traveling along this line. An observer here would say the light appears to be traveling along this line. So in order for them to agree, they would have to say that the light appears to be coming from this blue arrow. So that's where the image, or that's where the light appears to come from. That's not where the light actually comes from because there is refraction happening, but that's where our eyes will tell us that the light does go, or does come from. Hence, that's the location of the image. Now, I'm going to copy another image. It's basically the same thing, just with a little bit more detail. Oops. So this is the same setup. You have the same object, same image, and all of that. All we've done is we've shifted the optical axis down a little bit, just that way then the optical axis occurs where the light bends. It's neither here nor there, it's fine either way, but just that's all that's changing. And so now we can actually just ask the question, where does this light seem to come from? Like, we can calculate. So we can do some geometry. We know how sine of theta 1, this is the angle that the light comes into, this sine of theta 1. We know how sine of theta 1 relates to sine of theta 2. That's by Snell's law. So if sine of theta 1, which at least for the small angle approximation, which we're going to use very frequently in geometric optics, we almost always assume that the angle is small. We can assume that it's the tangent, sine and the tangent are the same. Then the height that the height, which is the distance from the optical axis to the top of our arrow in this case, this height h, we can relate the height to the distance to the object's position s by the angle, right? That would give us that the tangent of theta 1, which is this angle here, would be equal to the opposite over the adjacent, h over s, and that we're going to approximate that that's equal to the sine of theta 1. It's a fairly good approximation for small angles. Then we do the same thing for theta 2. By similar triangles, or by the law of intersection, it's some geometry law. If two lines intersect, the angles that they create are the same. So the two angles that I've drawn are the same. They're both theta 2. So we can relate s prime and h prime. In this case, it works out to be h. We can relate s prime and h prime to the sine of theta 2, or the tangent of theta 2, because they're the same. And so what we find is we get a relationship between the positions s and s prime, the position of the object and the position of the image. Now, by the way, it takes some work to actually show that they have the same height. It turns out that they do. It takes some work and it takes some more geometry, but they do have the same height h, which is why they're labeled the same way here. And so then you can just eliminate the h's in both cases, and you can solve for s. They have the same height h for the same reason that they have the same height h in a mirror, basically. All it does is it moves the location, moves where the object appears to be coming from. It doesn't actually change the apparent height of the object. I'll leave it up to you guys as an exercise to the listener, however, to prove that. But regardless, we can actually relate the apparent location of the light, s prime, to the original location of the source of the light, s, and the indices of refraction, n1 and n2. So let's talk about the sign conventions of this example. So in this case, we're going to use the same sign conventions that we used for a mirror. In this case, S is greater than 0 because the object is on the same side as the incoming light. So in this case, the incoming light, the incoming side, is this side, right? Because that is the side that the light is starting in. For S prime, well, what do we have for S prime? S prime is, the image is on the other side of the light. This is the outgoing side because that's the side that the light goes after interacting with the interface, with whatever it's interacting with, right? But S prime is on this side, hence S prime should be negative because the image is opposite the outgoing side. So when I say incoming or outgoing, it's just where does the light start and where does the light end? And so you can replace the side light is on before it hits the mirror with the side light is on before it interacts with the optic, whatever that optic might be. It might be a mirror, it might be an interface, it might be a lens, it might be whatever. It's just the side that the light starts on. The outgoing side is the side that the light ends up on after interacting with whatever it's interacting with. Okay, what's next? Well, what's next is we can talk about magnification now. So there is no magnification in a standard mirror, but let's actually define magnification. Magnification is a number that answers the question, how much does the object shrink or grow? So if we're talking about magnification in this sense, this is called lateral magnification. It has a very particular meaning. It's why I'm giving it a name. So let's say, so by the way, remember at the very beginning, I said that an object and an image both have three quantities. They have their position, their size, and their orientation. So far, we've only talked about position, but now we're going to talk about size. So say an object has height y, and the image has height y prime. By the way, we will always use prime to mean after the first interaction. Sometimes if we have two lenses in a row or something, or two mirrors, we'll have y prime, and y double prime. We'll have s prime, and s double prime, and so on. But we'll get to more complicated things later. Right, so say an object has, come on, scroll, has height y, and its image has height y prime, just for, like, through whatever, maybe it's a mirror, something, whatever. We define the lateral magnification m, that, actually I'll use this notation. This is how we define it. It is just y prime divided by y. And it turns out that y can be measured relative to the original orientation. If the object is in the same orientation, if the image is in the same orientation as the object is, then we would say that y prime is positive. If the image is in the opposite orientation that the object is, we'd say that y prime is negative. So in this case, m is greater than 0 if the image, m is greater than 1 if the image grows. So let me back up. That whole business about orientation I'll talk about more in a minute, but I want to talk about what happens when m is greater than or less than 1. So if m is greater than 1, then the image grows. If m is less than 1, then the image shrinks. And I'm actually going to put an absolute value here. And the reason I'm putting an absolute value there, by the way, is because m will tell us not only whether or not how the image grows or shrinks, but it'll also tell us whether the image is flipped or not. So for a mirror, as we've already seen, y prime is equal to y, and hence m is 1. And this kind of makes sense, right? A mirror doesn't make an object appear bigger or smaller, it just makes it appear further away. So it makes it look like it's smaller, but if like you were to somehow reach into the mirror with a ruler, the ruler would measure the same height, right? It doesn't make things appear, it doesn't like warp the image, it just moves where the image is. So this kind of makes sense that a regular flat mirror is not going to distort the image. What about for a refractor? So the example above, I made the claim, and I'm leaving it up to you guys to prove, but I made the claim that they have the same height. So in that example, y prime is equal to y. This is, by the way, only for a planar refractor. That just means that the interface is flat. Once you start curving the interface, everything goes out the water. So that would imply that m is equal to 1. So then the question is, why is it that objects look larger underwater? i.e., if you throw a penny to the bottom of a lake, it's going to look like it's bigger than it is, or the bottom of a sink or something. And the reason this happens is not because of the lateral magnification. The lateral magnification is still 1. The reason this happens is due to another type of magnification called angular magnification. And this is just a measure of how much larger it looks. Explicitly, it's a function of what we see. And so we can measure this. We can compute this explicitly. This is just theta prime divided by theta. So if the object would make an angle theta with your eye, and the image would make an angle theta prime with your eye, think like, if here's your eyeball, this object makes an angle theta, right? If the image is the same size but further away, terrible drawing, I know, then theta prime might be smaller. I'm going to be more explicit here. So theta and theta prime describe how much, quote unquote, space, or the correct language would be field of view. Those of you who are FPS players know what field of view is. How much field of view the object or the image takes up in our vision. So for a plane refractor, we know that m is 1. That's something that I've told you. Hopefully you believe me. We can talk about it later why that has to be the case. But what we also know is that s, absolute value of s, is greater than the absolute value of s prime. They're both, one of them is positive, one's negative. All I'm saying is that s, this is, by the way, in this particular plane refractor, i.e. if n1 is greater than n2. In this case, s is greater than s prime, i.e. the object is further from the interface than the image is. So that means that the image appears or looks the same size, but closer. And that implies that theta prime is greater than theta, which implies that the angular magnification is greater than 1, i.e. the object appears to get bigger. So just as a side note, if the image is flipped upside down, then that means that y prime is less than 0, and that implies that m is less than 0. And we'll see examples of this later. All right, so let's go back to the sign conventions. I'm going to scroll up and grab them so that I can keep adding. It's moving really slowly. Right. Sorry. Right, so I'm just going to add one more thing. So we're going to add the lateral magnification. We know it now has the name M, and it's positive when the image is upright, and it's negative when the image is inverted. And when I say upright, I mean it's in the same orientation as the object. Great, okay. So all of this planar geometry, when you have a regular reflector or a regular interface, it's all actually relatively easy to do. You just have to get out a protractor and think about things and do a little bit of geometry, but it's easy to prove, relatively speaking, and we can completely characterize all of this information in terms of just these three numbers. Things get a little bit harder once the interface starts to curve, which is what we're going to talk about now. Come on, scroll for me, please. There we go. We're going to talk about concave spherical reflectors. There we go. So reflector is just another name for a mirror. More complicated. So the geometry here for a concave spherical reflector is the following. So we have our central axis, and then we have a curved mirror. God, this is so hard to draw right. That's good enough. Importantly, an important spot for this particular mirror is if it's a segment or if it's a section of a sphere, then this would be the center. And this distance is the radius, right? So imagine that I could have completed this circle. That would have been the center of that circle. So it's the center of curvature is what it's called. So this is that axis of symmetry. It didn't matter where that axis was for a planar mirror or for a planar refractor because it's symmetric regardless of where you put the axis. But this is but for once you have curved mirrors, now there's a particular axis of symmetry. And so this is called the optical axis. And it's a useful reference point for anything with some sort of cylindrical symmetry, which this system has. So the first question that we can answer is, what if there is an object on the optical axis? So we're going to do the same sort of analysis. We're going to imagine that we put objects in different places, and we're going to try to understand where the light appears to be coming from. So the simplest case is, what if an object is on the optical axis somewhere? So I'm going to steal another picture. I'm stealing these pictures because these are hard to draw, and it's important that I get the drawings precise, so then I can convey the meaning. And I don't want to waste 20 minutes doing crappy drawings. Right, so here we've put the object in red. And if we just imagine that we put an eyeball, say here, then we can ask, where does the object appear to be? Where does the light appear to come from? We're going to put another eyeball here, just so then we can see. We can maybe look at it from another perspective to see where the lines intersect. And so the object, or the ray that goes from the object to the nicely drawn eyeball, well, it'll go to the mirror, and then we'll have to figure out what angle it reflects off of. Now we know that for any given mirror, the law of reflection is that the incident angle equals the outgoing angle. But how do you determine that angle when your mirror is curved? It turns out that the only thing that you have to reference is this this radial line. But note that that radial line is always perpendicular to the surface itself. So actually, we can use that central line, that dotted line here. We can use that as the line against which we measure angles. So in this case, this angle and this angle have to be the same. I know they don't look particularly similar, but they should. So we use the law of reflection there to determine that those two angles are the same. And that will let us draw this blue line, this dark blue line, all the way to our eyeball. Okay, so that tells us where one ray is. We need to do another ray to figure out where they might intersect. By the way, again, the blue line is the outgoing ray. The red line is the incoming ray. So again, we use the light red line. It reflects off much the same way. We would have a dotted line halfway, or at a, yeah, dotted, well, it is halfway between these two, hard to draw. So these two angles should be the same. And that would give us another line. And then we could find that point of intersection, and that would tell us where the object appears to be. Now, do note that for regular spherical mirrors, truly spherical mirrors, there's only really an approximation. It's only approximately an intersection. But it's good enough. So spherical mirrors make the geometry easy, but they do not perfectly reflect every single ray through the same point if an object is on the optical axis. You would need a parabolic mirror for that. Parabolic mirrors are very similar to spherical mirrors for large radius of curvature, but once you get to smaller radii of curvature, it gets less and less of a good approximation. So it's just a little tidbit that I thought I should mention. So what can we say about this radius of curvature, the distance between the mirror and its center? How does that relate to where the image appears to be? If you think about this just a smidge, it turns out that if the mirror curves more sharply, then the intersection point should move closer to the mirror. So this is something that you can prove, and in the paper textbook that I referenced in the syllabus, there is a geometric proof of that. I'll have to double check the online textbook. I don't know if he actually proves that statement, but it should be relatively intuitive anyway, because if you make the mirror curve more sharply, then the angles between the object and the normal get larger. And so that would mean that the reflected angle has to be further straight down, basically, which means that it'll be closer to the center of the mirror. Sorry, closer to the mirror itself. Another question that you might ask is, what if the mirror's center is on the other side, i.e. not the outgoing side? Because remember, everything has a sign convention. So that would be like we have a mirror shaped like this. Again, we have our optical axis. Maybe we have our object here. But in this case, the center might be, I don't know, here. And this is the radius r. So what happens then? Where does the object appear to be? Well, let's put an object somewhere else. Let's put it here. So let's just start drawing rays. So a ray like this, well, we know that the interface normal, has to pass through there. So that means that this would also be an interface normal because it has to be perpendicular. So those angles would have to agree by the law of reflection. And then we can do another one, maybe up here. Draw that through, continue it on. Again, these are not perfectly straight. And then these angles would have to agree. So maybe something like this. So we would have reflected light going in those two directions. Now those don't intersect. What they do though, is if we extended them, they would intersect, and these should intersect, you know, right about there. It's not a perfect drawing, but the idea is, in this case, whereas the image when the object was on the same side as the curvature was in the same place, here now the image, here's the object, is on a different side. So again, if this mirror curves more, again, the image moves closer to the mirror. It's for the same reason. You can think about this just a smidge, but the idea is that if it curves more, then the angles get larger, and so the reflected angle will be even more parallel to the surface of the mirror. And so what you get is if you had a really steeply curved mirror like this, then this will get like shot straight down if you were to extend it because of those reasons, basically. And so you'll see that it gets closer rather than being further out if it was curved less dramatically. I'll let you guys think about that a little bit. I don't want to spend so much time on it. And so the fact that this happens for both cases where the mirror is curved on the same side as the object and the mirror is curved on the opposite side of the object would suggest that they probably obey the same equation, perhaps just with one of the variables changing signs. And we're going to get to that. In fact, the equation that they both obey is 1 over s plus 1 over s prime is equal to 2 divided by r. This is the, I'm not going to give it a name because we're going to generalize it in a minute. But this is the equation that they both obey. They both obey this equation. And this is derived from the fact that if you curve the mirror more sharply, then s prime has to get closer to the mirror itself, has to get closer to 0. The only difference here is that they have different signs for r. In the case of the concave reflector, we have the equation, or we have r is greater than 0. And for the convex reflector, by the way, this is the convex reflector. It's just the one that's not concave. And the way you think of it being concave is there's a little cave that's formed here. That's how I remember it. Convex is just not concave. For a convex reflector, we just have that r is less than 0, but they obey the same equation. They're both still mirrors. And in fact, for a planar reflector, that's equivalent to r being equal to infinity. And it doesn't matter whether it's positive or negative. And so you just get that 1 over s plus 1 over s prime equals 0, which just should lead you to conclude that s is equal to negative, or s prime is equal to negative s. So we have another sign convention now. I told you we'd be adding to this. Because now we have to talk about what r does. When is r positive, when is r negative? And the reason that's not what I wanted. The reason why we want to define all of these sign conventions is that we can memorize as few equations as possible and just apply the different conventions to the different cases. We could have had different equations for those two separate reflectors, but that would have meant that we would have had to, one of the equations would be positive, one of the equations would have a negative sign, and we would have had to memorize 2 equations. By just memorizing one equation and then knowing the sign conventions, it makes it a little bit easier to write a general equation that applies for all of these things. There we go. So in this case, we have to add another symbol. This is the radius of curvature. It's called r. And so in this case, we call the radius of curvature positive when the center of the sphere is on the outgoing side. And it's negative when the center of the sphere on the other side. So you can see that that agrees with the convention that we used here. The center is on the other side of the outgoing side, because the outgoing side is this side in this case. So r would be negative. In the concave reflector, the center of curvature was on the same side as the outgoing light, which means that R would be positive in that case. And they both obey this equation. Again, you can look up a derivation or you could try to derive it yourself. I'd be very proud of you if you did so. It's not particularly difficult, but it takes some work. Now, this is great and all, but sometimes we just like to use geometry, and I should specify a very specific geometric feature that mirrors have. So for mirrors, there is a special reflection, i.e., if you have light coming in a very particular way, the light will always do the same thing in a very predictable manner. So this is how we determine the focal length. I'm going to steal another picture. Copy that. So again, let's assume that we have a curved mirror. Let's say it's concave. If you have light that comes in parallel to the optical axis, like these red rays are doing, it doesn't matter where they hit the mirror. They always they will always pass through the same point. They pass through this point that is halfway between the mirror and its center. In fact, this is even true for convex mirrors as well. It's just the light will appear to pass through the point halfway between the mirror and the center on the other side. They will spread out rather than come together, and so you'll have to trace them back, and they'll appear to intersect at that point. So this point has a name, and it is called the focal point. It is always, for a spherical reflector anyway, for a mirror, it is always halfway between the central point and the mirror. Now, so that is to say, F, which is what we call the focal point, it's equal to R/2, as you guys see above. And so we call F the focal length. And it is the distance from the mirror to the focal point. Now, for mirrors, this is nice, but for lenses, it's even nicer. That's why we introduced this language. But in fact, even just for mirrors, it simplifies our mirror equation. I'll call this the mirror equation. So we don't want to write things in terms of this radius of curvature R. We'd rather write it in terms of something that's easily measurable. So how might you measure the focal point? Well, you shine incoming rays parallel to the mirror. You see where they intersect. Easy peasy, you've figured out where the focal point is. A little bit harder to measure the center. So what it does is if we rewrite the mirror equation in terms of this focal point, it simplifies it. Makes it 1/s plus 1/s prime equals 1/f, the focal length. And so just like the radius of curvature R, focal length can also be negative. So we're going to add that to our sign convention table. It's getting slower and slower as I keep copying and pasting. Okay, so let's add that to our table. So we have focal length. Call that F. And the focal length is positive when the focal point is on the outgoing side. And we call it negative when the focal point is on the other side. Great, okay. 5 things on our table. We're gonna continue to use this table, but I think that that's the last thing that we're putting on the table. Let me just double check. Yeah, I think that that's the last thing, but we're gonna now use these in more general terms. So we've learned how rays interact with mirrors, but it turns out that there's actually a relatively neat set of tools that will let us solve a lot of these problems geometrically. And that is called ray tracing. This set of tools is called ray tracing. And you may have actually heard of ray tracing in computing if you're into computers and into graphics and stuff. It's essentially the same principle. So what we're doing when we ray trace is we follow special quote unquote principal rays. Underline that because that's a useful term. From an object until they become outgoing rays. So in this case, why might we want this? Well, if we know what direction the outgoing rays are going in, then the observer can conclude where the outgoing rays can appear to come from. So far I haven't said anything new. But the idea is, at least like in computing, and what we've done this entire lecture, is we basically just drawn rays from an object and then just put observers everywhere and see and ask. You draw a whole bunch of rays out, you make them become outgoing rays, you figure out which direction they propagate in, and then you just find their point of intersection, and that's where the observer would see that thing. And that's what computers do. That's how they ray trace to get good graphics. And this is how an observer sees an image. But when we talk about ray tracing with pen and paper, we're not talking about drawing every single ray like a computer would. A computer would draw millions of rays for a single object. We only draw a few. So the principal rays, they're not physically special. There's nothing actually special about them. But they are just convenient tools. So it's not like a principal ray is a real thing. It's just a useful way of classifying the different rays that can come from an object. And because we know that certain rays are going to do certain things. And so if we can classify which rays those are, then it'll be easier to draw them and solve these problems geometrically with a pen and paper. So let me copy another image. This image is very loaded, meaning it has a whole lot of information on it. And this is going to be an image that you should get very friendly with. Let me make it bigger so then it's a little bit easier to see everything. So what appears on this in this image is, remember, red is the object and the incoming light, and blue is the reflected light and the image. So there are 4 red rays coming from our object. 1, 2, 3, 4, right? And that means that there's going to be 4 outgoing rays. Now, for a mirror, there are 4 principal rays, and in fact, these are the 4 principal rays. So the first principal ray is the ray that travels from our object in a direction parallel to the optical axis. So remember, the optical axis is this horizontal axis here. So we draw a ray from our object that travels parallel to our optical axis until it hits the mirror. And then the question is, where does it end up? How do we figure that out? Well, we already know from the definition of the focal point that a ray that's parallel to the optical axis always intersects through the focal point. So our first principal ray, we draw it from our object, and then we draw it to the focal point, and then we can continue it on. So that tells us what the first principal ray does. So that's useful because it means that we can always draw that ray, and it's very easy to draw physically. Okay, what's the next ray? The next ray is this one. It's labeled number 2. That ray is the ray that hits the center of the mirror. So you would draw a line connecting the object to the center of the mirror. We know where the center of the mirror is because that is the location that the optical axis intersects with the mirror. And then because the law of reflection tells us that the incoming and outgoing angles have to be the same, and we know what the normal is to that surface, it's the line that goes along the optical axis, we just know that we have to match these two angles, the incoming and outgoing angles, relative to the optical axis. So the second principal ray, just to clarify, is the ray that starts at the object, goes to the center of the mirror, and then reflects off at the center of the mirror, by the way, the center of the physical mirror, not C, the center. It reflects off at the same angle relative to the optical axis. So these two angles should match. So if you had a protractor, you could get that angle, you can measure that angle, and then you can figure out what angle the center comes out with. The third principal ray is the ray that goes through the focal point. So it starts at our object, it goes through our focal point, so I would draw a line connecting them, and then I would just let it go until it hits the mirror. Now, because mirrors are time symmetric, meaning if you send if you, how do I want to phrase this? You could just as easily send rays backwards starting from the outgoing ray, and it'll reflect back to the incoming ray. So what this means is that if you send a ray that goes through the focal point and it hits the mirror, it'll reflect off parallel to the optical axis. And that's exactly what we're observing here with this third principal ray. It goes through the focal point. So we draw a line connecting those 2 points all the way to the mirror, and then it reflects off parallel to the optical axis. All right, we just have one more for mirrors. The last one for mirrors is the ray that passes through the center. So you start at your object, draw a line to the center, and then continue it. And then because the line connecting the mirror and the center is a 90-degree angle relative to the surface, it'll just reflect back in the same direction. So this ray just goes from the object to the center, to the mirror, and then back in the same direction. And so with all 4 of those rays, you'll see, if you did it perfectly and you're making the correct approximations, they will all intersect at a point. And that point will tell you how high above the optical axis the top of your object is. It'll tell you both this distance and its position. So basically, by ray tracing, you can determine the height, you can determine the position S as opposed to S, or S prime as opposed to S, and it'll tell you whether it's inverted or not. In this case, it is inverted because it's upside down. So those are the 4 principal rays for a mirror, and they just as equally generalize for a convex mirror. But in this case, a lot of these things, for example, where the how do I want to phrase this? Right, for the first parallel, for the first principal ray, it can't pass through the focal point because the focal point's on the other side. So you'd have to draw a line from the mirror to the focal point and then continue it to figure out what direction it would actually bounce off of. So for a lot of these, for a convex mirror, you have to trace them through where they should go and then trace it through on the other side of the mirror to figure out where the light actually does go. So in this case, we can actually use a ray trace to understand how magnification relates to position. For a mirror, anyway. Magnification relates to position. So the point is that you always have access to these 4 principal rays. You really only need 2 to figure out where they intersect. But sometimes one is more useful to use than another, so it's nice to have all 4 of these in your arsenal. Let me go steal a picture again for what I mean when I say that we can understand how magnification relates to position. So here we have our object in red. And so we can use one of the principal rays, in particular the ray that travels through the the ray that travels to the center of the mirror, to learn something about the magnification. So first, we would figure out, we could use, say, this ray, the one that passes through the focal point, to figure out where the object is, because we need to know that. And then once we have where the object is, we can also figure out the height of the object by using similar triangles, because the triangle formed by the image, the optical axis and the hypotenuse, right triangle, let me see if I can draw a better one. That's a similar triangle to the triangles formed by the red lines, right? They have the same angle there, and they are similar. So that tells us something about the magnification. The magnification, remember, which is y divided by y prime. In this case, sorry, divided by y prime divided by y, this is equal to negative s prime divided by s. And that's just a relationship about similar triangles, right? Let me erase these lines. So the ratio of the ratio of the lengths of sides are the same for similar triangles. So the ratio of this line to this line is equal to the ratio of this line to this line, i.e. the ratio of y prime to y is equal to the ratio of s prime to s. I stick a negative sign there because we see that the image becomes inverted. Indeed, this is actually just the equation for magnification for a mirror, and for a lens, for that matter. Now, I just want to note something that, in case it wasn't clear, and I'll just say it, it's in the lecture notes. If you put your eye between two principal rays, like looking up at this picture, if you put your eye, say, here, you still see the image. You still see the same image as all the other eyeballs would see, at least as long as nothing's blocking the light. Like if you have a screen here that's blocking the light, then you're not going to see anything. But the point is the principal rays aren't like, it's not like you can only see the image from those particular locations where the principal rays end. You can see the image everywhere. It's just the principal rays are a useful tool to figure out where the image is. All right, next, let's talk about convex spherical reflectors. So if R is less than R naught, or than 0, what do the parallel rays do? So let's draw, let me steal another image. So let's start off with the first principal ray. The first principal ray is the one that goes in parallel. So we start off with rays coming in parallel along the optical axis. Maybe they're coming from like two objects, like an object here and here. But let's just look at what happens to rays that enter parallel to the optic axis. In that case, we know that these are principal rays. So we know that they should pass, like the reflected rays should pass through the focal point. But that can't happen because the focal point is over here and the light can't get there. So instead what happens is we draw it as if the light did get there, and then that will tell us the direction that the light gets reflected back off at. So what you do for these convex spherical reflectors is much the same that you did when we were ray tracing before. You extend the rays, and then you extend the rays to the other side of the mirror, and that will tell you what direction the rays go. So it's still true that this first principal ray, if we had an object, that this first principal ray reflects off in a direction that passes through the focal point. It just passes through the focal point on the wrong side of the mirror. Similarly, if we look at the second principal ray, sorry, the second principal ray is still the same. If we look at the third principal ray, the one that passes through F, well, what would we do in that case? Actually, do I do this example? Yeah, I actually do this example. So I'll do this in a minute. So let's just, this point here is a point of apparent divergence. So if these two rays were coming in, it would look like you have light coming from this point. So where does the mirror equation say that the image is? Well, the mirror equation is 1 over s plus 1 over s prime, which is equal to 2 over r. or equivalently 1 over f. And 1 over f in this case is negative, because f is negative from our sign conventions. We're going to assume that s is positive. That's almost always true. That implies that s prime is less than s as absolute values go, and s prime is negative. So for convex spherical reflectors, it is always true that the image is on the non-outgoing side. And it's also always true it is closer to the mirror than the object is. So just to back up and slow down a little bit, if we're solving for s, so 1 over s plus 1 over s prime has to be equal to 1 over f. Now 1 over f is negative. So if s is positive, then 1 over s is positive. So we have that 1 over s prime equals 1 over f minus 1 over s. This is negative, this is positive, so this whole thing is negative. Automatically, that tells us that s prime is negative. And then you can actually relate their absolute values, and you'll find that s prime has to be closer to the mirror than s is. Sorry, the image has to be closer to the mirror than the object is. And that's just because, basically, this number has magnitude greater than the magnitude of 1 over s. Simply because this number is 1 over f is some negative number, and then we're subtracting off 1 over s from it, so it's going to be even more negative than 1 over s is positive. And if you don't remember that argument, you either look back at the lecture or derive it yourself. Okay, so that's great. We've determined that we've determined some stuff about where the image is. Now the question is does ray tracing, which I've hopefully convinced you is a great tool, does the ray tracing, do the steps used in ray tracing agree with what we've just derived? I.e., is it true that the image is closer to the mirror, and is it true that the image is always on the other side of the mirror? Well, let me steal another diagram, which will make these ray tracing for spherical reflectors more straightforward. Sorry, for convex spherical reflectors. Let's blow this up a little bit. Nope, come on. Okay, here's our object in red, as usual. First ray is always parallel to the optic axis. We know that it reflects off in a way that the line would touch the focal point. So we would draw a line from the mirror to the focal point. Now, that's on the wrong side. So if we want to figure out what direction it actually reflects in, we just continue it on the correct side. But if we want to figure out where the image is, we're probably going to need to continue it anyway. So it's continued in dotted blue. Okay, what's next? Second ray is the ray that hits the center. That's all that just hits the center and comes back. Sorry, it hits the center and it just comes back at the same angle. Again, these two angles are the same. That one's always easy. It just is what it is. We might want to continue it back though to figure out later. So let's do that. Again, it's continued on back through blue. Next, third ray is the ray that's aimed at the focal point. In this case, we can't actually fully get to the focal point, right? We would have to pass through to get to the focal point. But we know that if it's aimed at the focal point, then it should come out parallel to the optical axis. That's just what happens. So if we wanted to be precise when we were talking about the principal rays before, it's not that it passes through the focal point. It's that it's aimed at the focal point. It's just that if the focal point's on the same side as the light, then it will pass through the focal point. And so then it comes off the optical axis. And again, if we want to see where they might intersect beyond the mirror, we have to continue it on through, again with the dotted line. And then the last one is the one that's aimed at the center. Again, doesn't have to pass through the center, just is aimed at the center, in which case it reflects back in the same direction. And so what we see by looking at all of these dotted lines in blue, we see that they would converge right about there. And so indeed, it is true that the image is closer to the mirror than the object is. This distance is certainly larger than this distance. And it's also true that the image is on the other side of the mirror. So the conclusions that we could draw from the mirror equation up here agree with the conclusions that we get from the ray trace, and that's a good thing because it means that our math agrees with what we expect from reality. So remember how we related the height of the, we determined the magnification in terms of distance? Well, the same is true here. Because we still get, because for a convex mirror, the ray that travels through the center, where is that? It's this ray. Because that still forms because it still goes back with the same angle, these two triangles, come on, I can draw better than this. These two triangles are similar. They have the same angle there. And they're both right triangles. So that means that we can relate the height here again to the height here. Sorry, y. We can relate s and s prime. So again, we find that m is still equal to negative s prime over s. That's still true because we still have a similar triangle argument. And this implies, because we know in this case that it's upright, in the case of a convex mirror, and i.e. s prime is negative, this implies that m is between 0 and 1, because s prime is less than n in absolute magnitude and it's negative. So what we learn from this sort of geometric argument, we learn that the image is smaller but upright. So the logic here, by the way, just to clarify, is let's just assume that this formula applies for all mirrors, because you can use the same argument. Then we can use this relationship, we can use the mirror equation and this relationship regarding the magnitude to learn that the image is on the other side of the mirror, it's closer to the mirror, it's smaller than the original object, and it's upright. And then we can go and check, does that agree with the ray trace? And indeed it does, which again, hopefully shouldn't be surprising because I wouldn't be teaching you it if it wasn't correct. So the whole point is that the equations that we've been using agree with this ray tracing. So both methods are valid for understanding, I should erase these now because they're gonna move around. Both methods are valid for understanding what happens in some sort of optical scenario. I.e. this agrees, and I'll be done in a minute. This agrees with ray tracing. So that tells us about the lateral magnification, but what about the angular magnification? The angular magnification doesn't just depend on the image, because it depends on how close the image is to you. In fact, it also depends on where you are, or where the observer is. If you're located at the mirror, if your eyeball is touching the mirror, then it's always the case. How do I want to phrase this? Yeah, this is true. If you're at the mirror, then it's always the case that the angular magnification is 1. And that's just because of the same similar triangle argument. But as you move further from the mirror, the angular magnification becomes less than 1, i.e. it looks like it shrinks. And that's just because the angle gets smaller. How do I want to phrase this? If you're standing here, then the similar triangle argument works in your favor. But if you're moving here, it works less in your favor, because now the image is here, so the image is getting smaller and the object is getting bigger, and so on. So the angular magnification is not something that is inherent in the system itself. It very much depends on where the observer is. So that's why, even though angular magnification is the thing we experience, it's not particularly useful in a lot of cases. For some things it is useful, like a telescope, by definition, has to increase angular magnification. Otherwise you can't actually see more of it. It doesn't look larger to us. But we design our telescopes so that they incidentally increase angular magnification. Anyway, I'm over time, so I'm going to stop there. I don't want to drag you guys over. And I think we only have like 3 pages left of today's lecture, and then I think Friday's lecture is only 6 pages long, so we should have plenty of time.